Welcome to online training session, day 6, Topology Optimization, part 1. I have divided the complete Topology Optimization training into two parts. Today I am going to take the tutorials which I have divided in the part first, and then in the next session I am taking the rest of the tutorials in the another part, that is part 2. So this is the training series details. We have ended with the theory of FEM, 1D meshing, 2D meshing, 3D meshing, analysis and post-processing. Now we are in the day 6 session, that is topology optimization. The rest of the session which I am going to cover are topography, size, shape and composite optimization. So the topics which I am going to cover in this topology optimization part 1 are: first, we'll see the design concept for a structural C-clip, then design concept for a structural C-clip with minimum member size control. So there is one more option which we can use in HyperWorks. Then design concept for an automotive control arm, then increasing the natural frequency of an automotive splash shield with ribs, then control arm topology optimization with draw direction constraints. So with these tutorials we will try to familiarize ourselves with the different tools available or different panels available in HyperMesh to perform optimization. Then we will see the spot weld reduction using C-weld and 1D topology optimization. The last tutorial which I am going to take in this training session is pattern repetition using topology optimization. So let's start with the first, that is design concept for a structural C-clip. The topology optimization techniques yield a new design and optimal material distribution. Topology optimization allows designer to start with a design that already has the advantage of optimal material distribution and is ready for design fine-tune with shape or size optimization. In this tutorial, topology optimization is performed on a model to create a new topology for the structure, removing any unnecessary material. The resulting structure is lighter and satisfies all design constraints. So the design, basically topology optimization scoop out the material from the actual component and gives you the new component with lighter, with less material. So this will help us to get a material distribution, to get lighter components. And also you can put some constraints so that it satisfies all the parameters, like it should not, if you put a constraint like it should not go beyond this limit of stress or that much displacement or this much amount of minimum strain it has to achieve. So that is also possible, we will see that. The optimization problem for this tutorial will state it as my objective is to minimize the volume fraction. My constraints are the translation along y-axis for a node A should be less than 0.07 mm and translation in y-axis for node B should be greater than minus 0.07 mm. My design variable, the density of each element in the design space. In this tutorial, we will see how to set up the model in HyperMesh for the optimization, analyze the baseline model to see the stresses and displacement before optimization and after optimization, set up the optimization problem and then post-process the results using Hyper-V. So we will start our training session with this. So we'll open the HyperWorks Student Edition version 12. So version 12 is released now, so you can use that. So we'll use that. We'll select once you will open, you will select. You have to select the proper user profile. Otherwise, some of the options you may not, you will not see that options if you doesn't select the user profile correctly. So make sure you select the user profile correctly as OptiStruct. To select the user profile, I'll show you how to select the user profile. Click on Preferences or click on this, the icon of a human. Click on this click on preferences and select user profile. This is the one way to select the user profile, and the other way is to click on this human and select the user profile and click OK. So it will load the templates related to the OptiStruct optimization user profile. Then we'll start with setting up the model in HyperMesh. So we'll open the model of C clip. So we'll go to open. So this is my model, which is already mesh model. As you can see, we have two components. One has the surfaces. On the surfaces. So one component has the surface, the surf component, and the other one has the elements, as you can see. So my meshing is already done on this component. So we'll directly start with the optimization process. So first we will start creating with material properties and assign them to the component. So we'll start with the material creation. So we'll go to material collector icon, click on material collector icon, enter the material name as steel, select the color, select the type as isotropic, card image as matte 1, click on create edit and enter the values of E, nu and rho. As I already shown that how to identify the values of E, nu, rho, G, A, TREF, G, ST, SC, what are these values stands for, what are these values stands for, everything you can find it on help related to all the card images. So I quickly define what is the difference between matte 1 and matte 4. The matte 1 and matte 4 card image has a thermal coefficient difference. So if you want to perform the thermal analysis, you use matte 4. Otherwise, you can use for basic static analysis, you can use matte 1 card image. So on the model browser, you can see my material has been created. As on the model browser, you can see that. Now the next step is to create the property. So on the right hand side of material collector icon, you will find the property collector icon. So click on property collector icon. Enter the property name as, say, property shell. Define a different color. Select the type as 2D because these are the 2D elements, 2D shell elements. Enter the card image as P shell. Select the material which you have created earlier. Then click on create edit to edit or to provide the thickness of the shell elements, and we'll select the unit thickness. Then click return to exit the property collector icon, and again click return. So on the model browser, you can see my property is also created. Now we will assign this property to the component. So on the left hand side of the material collector icon, you can see a component collector icon. So in component collector icon, select the radio button as update. Click on comps, select the comp shell, click on select. From the no property, toggle it down from this, toggle it down to property and select the property which we have created earlier. And click on update. So my elements will get a property and material as per my requirement. We can check it from here also. If you click on this drop box, so by property, if you click, you will see the color of the property on the element, and by material you will see the color of the material on the elements. So in this way you can see the colors. I will again click on by component. Now the next step is to define or to apply the constraints and forces, that is the loads on that on my model. So next we will see how to create two loads, that is constraint and force. So click on load collector icon on the right hand side of the property collector. You will find a load collector icon. Enter the load collector name as force. Click on the color palette and select the force and say no card image and click on create. Then enter the load collector name as SPC. Click on the color palette, select the different color from the force one and click on create. So SPC stands for single point constraints. So we are going to apply the single point constraint on this model. Then we will apply the constraint on this model. So to apply the constraint on this model, first we have to click return to exit the load collector panel. Then go to analysis page. On analysis page, click on constraint. We will apply the constraint on this node for 3 degrees of freedom. We will apply the constraint on this node for the 3rd degree of freedom, that is translation along Z. And on this node we will apply the constraint for 2nd degree of freedom, that is translation along Y. This is as per my model requirement, so it may differ as per your model requirement. So that is this is for the basic static analysis. We haven't done anything related to the optimization. Then we apply the forces on this structure. So we'll click return to exit the constraint panel. Go to model browser, load collector, right click on force and make that as the current component. So my forces will go to that component. And on the analysis page itself, we will click on forces. Select the node like node A. Enter the magnitude, let's suppose 1000. In y-axis, click create. We'll magnify it, say 10 or 7. Then select the other node with opposite direction of force. Say create. So I have created two forces. One is in positive Z direction, one is in negative Z direction. So I have applied the constraint and forces. Now the next step is to create the load collector, the load step. So that I can define the system, that exactly what type of analysis I want. So I will go to create load step. I will go to analysis, load step. Enter the load collector name, say opposing forces. Select the type as linear static. Check the box in front of SPC and check the box in front of load. Click here and select SPC. It will tell you the number of SPC, that is 2, and force, that is 1. So this is the load collector number. Then click on create. So on the model browser you can see a load step is already now has been defined for my model. So I will go for the analysis of the C clip to see what is the values of stresses and displacement, and then we'll move for the optimization. So I will save this file. Basic analysis. I will name the folder and save this file. To perform the analysis, I will go to Analysis, OptiStruct, select the Export option to All, Run option to Analyze, Memory option to Default, and click on OptiStruct. This will launch my solver window. Then click on Results to view the results in HyperView of the stresses and displacement. Of the complete model, for the complete model. So we'll click on Contour. This icon is the contour icon. Select the result type as displacement. We are more interested to see the displacement values. Go to Measures and check the box in front of static mean max or on the both minimum or maximum. This measure option will help us to see the minimum and maximum value. And you can also go to this H frames and increase the magnitude, say by 10. So you can see this is the displacement of original to the displaced model. In this way it will displace. Now we will create a setup for topology optimization for this model, or you can see the animation plot also. If I change it, the animation will increase. So this is the animation. I will pause it, click close to close the HyperView player. Again we will close this. So now we'll start the setup for topology optimization. So I'll again show you how to edit the forces. Somebody asked me to show how to edit the forces, so I will edit it. So go to edit the forces, go to Analysis, Forces, select the force which you want to edit. Let's suppose if I want to change the magnitude, I will change the magnitude from here. Click on Update, say Update. Similarly, I can change the magnitude of this, say Update, Update. So in this way I can change the magnitude. I will again solve it and see the results. Simply we can just, anytime we can edit any values of force, constraint, anything, and then view the results. So we will close this XY mode, go to Contour, say Displacement Apply, go to measures, static mean max. So this is the displacement value. It's very less, as you can see. It's 0.025. So now we will again close this hyper view, the means result viewing, the post processing part, and close the solver part. Click return to exit the solver window. Now we will see how to set up the optimization model. The finite element model consists of shell elements, element properties, material properties, and loads and boundary condition has been defined, as you can see here. Now we'll see the topology optimization will be performed with the goal of minimizing the amount of material to be used. Typically, removing the material in an existing volume with same loads and boundary condition makes the model less stiff and more prone to deformation. Therefore, we need to track the displacement, which represents the stiffness of the structure, and constrain the optimization process such that least material necessary is used and overall stiffness is also achieved. So as we have already discussed here, we are going to restrict the displacement of node A and B to 0.07 mm so that we will get at least some amount of displacement, not less than that. So this is my minimum required displacement. I should not go below that. Somewhere near it's okay. The force in the structure are applied at the outer nodes of the opening of the C-clip, making those two nodes critical location in the mesh where the minimum displacement is likely to occur. So in this tutorial, we will apply a displacement constraint on nodes so that they would not displace more than 0.07 in y-axis, either positive and negative. So we will start creating the topology optimization design space. So to enter to topology optimization or to any optimization process, click on analysis page. On analysis page, click on optimization. So in optimization, we first create the design variable, that is on which element we should remove the elements, or which are the areas from where the software can remove the elements. Then we create the responses, like we create load collectors in static analysis, that what are the what is my objective and what is my D constraint, that we will create here. So there are 4 steps in any optimization. First, like DRDO, I will write it here. First is design variable, responses, D constraint, it is also called as constraint, and objective. Here we define where on which area the element should be removed or change of the space. Here we define different responses here we define the responses for the D constraint and the objective. So my objective may be to minimize the volume, minimize the stress, minimize the displacement, minimize the frequency, maximize the frequency. Anything can be my objective, and my constraint can also be anything, like I want the minimum stress should not go below this, or maximum stress should not go below that. Maximum stress should be somewhere around 200 Newton per mm square, something like that. So that is also possible. So first we create the design variable. So we'll click on topology, the first column, first row option, that is topology in optimization panel. Click on create and enter the DESVAR, stands for design variable. Enter the design variable name as the shell. Select the type as P shell, that is the shell elements. Keep the base thickness as the default, that is 0. Select the property which we have created and click on create. So on the model browser you can see my design variable D shell has been created. Now we will create a volume response. So to create a response, we will go to, on the same panel we will go to response, Enter the response name as volume fraction. Select the response type as volume fraction from the drop box menu, volume fraction. Keep all the other parameters as it is and click on create. So on the model browser you can see optimization response first is created, that is volume fraction. Now we will create two more responses for my constraint. This is my objective. Volume fraction is the objective. And for the D constraint I will create two more responses as upper displacement. Select a response type as static displacement. Select this node and select the degree of freedom 2 because it is translating only in y-axis. Click on create. Similarly, I will create one more as lower displacement. Select the below node with the same degree of freedom. I will click create. So my two responses has been created. Now we'll create the constraints, that is D constraint for my optimization process. So I will click return to exit the response panel and go to the D constraint panel just below the response panel. You can see here. Enter the D constraint as C upper, that is upper value. Check the upper bound and enter the value of 0.07. It should not go beyond 0.07. Select the response as upper displacement. Click on the load step and give the load step which we have created. So it will take the value of the static analysis and then try to see whether we can remove the material of my constraint value or not. See here what it does. It restricts the displacement to 0.07. But due to the force, if the displacement is more than that, so it will not solve. So it has to be, we have to give them a basic load step also, which we have. Whatever analysis we did earlier, we have to provide the load step of that. So it will perform that analysis again, along with the optimization. So we'll click on create. So on the model browser, you can see my optimization constraint is defined. Now similarly I will create one more as C lower. Untick this, check the box of this and enter the value as 0.07. Select the response type as lower displacement. Load step will be the same. Select and create. So my two constraints, that is the upper constraint of 0.07 and the lower constraint of minus 0.07 is being defined. Now I will define the last step of the optimization, that is objective. So my objective is to minimize the volume fraction and click on create. So I will again show you from where I entered to objective panel. So this is the objective panel. Select what exactly your objective is, to minimize, to maximize, to minimize the maximum value or to maximize the minimum value. So here my objective is to minimize the volume fraction. So select the volume fraction and click on create. So on the model browser you can see your objective has been created. So on the model browser we can see whether we have done the DRDO process or not. So design variable, responses, D constraint and objective. So we have done all these things for to set up the optimization problem. Just like MPCLL for the static analysis, that is, there are some formulas too, so that the error margin reduces. So we will save this file and see the results of the analysis. So I will enter it, topology optimization, save this file. Go to analysis, OptiStruct, that is the solver to solve the optimization. Select the export option to all, run option to optimization, memory option to default, and click on OptiStruct. It will start the solver window. So you can see my optimization in optimization process. The message optimization has converged and feasible design achieved. That is the most two important comments which has to come. So as you can see, we can see that comments. I will click on results. So first we will see the displacement value. For the last iteration. This is my element densities. And the element thickness values. So this is my new design for my analysis perspective. And if I split the window, so here we will get two models, that is C-clip DS HTD, C-clip S1 HTD. S1 is the optimized file, DS is the base model. So it will automatically load that model, so I will load the S1 file, say apply. Go to contour, and here you can see the displacement. So this is the proposed design. If I go to ISO and change this value, so 0.35 enter. So this is the design. These only the material required to achieve the displacement of 0.071. So with this design, it has achieved the displacement value of 0.071. So in this way, my optimization software provides you the different designs, and you can also see by moving this current value to how much material it's scooping out. So you can also change the values, like this much material if I want, you can also take, or you can remove some more. So the red is the most critical, the blue is the least critical material. This is the element density, and this is element thickness. So where the element density is high, that area you should take care of. So you should have a blue region somewhere on your model. The light blue region at least you should have. It should not be like this, so it may or may not fail. But with the blue one, the chances of getting failed will be less. not the dark blue but the light blue one, yes. So in this way we have ended with the first tutorial, that is the design concept for structural C-clip. I will close this. I'll also go to presentation here and we'll move to the next tutorial, that is design concept for a structural C-clip with minimum member size control. So there is a small difference between these two. We'll for this model, on the same model we'll add one more thing as the minimum member size control parameter, so that the members which we have get after the topology optimization will be of some minimum thickness or minimum length or minimum width. So that we also that is also we can put. So performing topology optimization earlier in the conceptual design stage results in the generation of good baseline design and contributes to a shorter design cycle. One challenge with post-processing topology optimization result is that the result may have several intermediate density elements or checkboard patterns which can be interpreted either as solid members or as a void. If these semi-dense elements are interpreted as thin members, the final design is harder to manufacture. So, OptiStruct offers a minimum member size control method which provides some control over a member size in the final topology design by defining the least dimension required in the final design. It helps achieve a discrete solution by eliminating the intermediate design density elements and checkboard density pattern, resulting in discrete and better reinforced structure which is easier to interpret and also easier to manufacture. This optimization problem applies the technique of minimum member size control on the element of the model to achieve a discrete solution. So the following exercise is an OptiStruct topology optimization and covers the following process. We'll see how to import the FEM file into HyperMesh, set up minimum member size control problem using HyperMesh, and post-process the final result. So I will again go to HyperWorks. I'll close this. So one way is I can save this file, click on New, import a different file, click on Import Solver Deck. Select Solver Deck as OptiStruct, click the file, import this model, so everything is defined in this model as you can see. So this model is available in the tutorial file, or you can use the model which we are using or which we have done in the tutorial first, topology optimization. So we will use the same model, and just changing one of the parameter will help us to get the better control over the minimum member size or the manufacturability. So we'll directly move to the optimization panel. So analysis, optimization. Rest of the things are already defined. As you can see, material properties, component, load collector, load step, design variable, responses, deconstraint and objective, everything is defined already. So I will go to optimization panel. In optimization panel, I will click on topology optimization. But before that, we will see the distance between the element or average element size. We will try to find it out, and accordingly we will put the average element size. So either go to geometry page, distance panel, or press F4 from your keyboard and check the distance between any two elements. So it is always coming as 2.6, 2.5. So average element length, you can see it's somewhere around 2.5. Wherever you can see, it's somewhere around 2.5. So we can say my average element size is 2.5. So the average element size of this model is about 2.5. So it is recommended that the minimum dimension value be 3 times larger than the average element size unless the element's mesh is aligned, in which case it can be 2 times larger. So the general rule for minimum member size is that it should be 3 times the size of the average element size. So whatever the average element is, it has to be of 3 times. So go to topology optimization, select parameters, click on review. So we will select the design variable as which we have created earlier. Enter the value of minimum member of to minimum dimension and enter the value, let's say 5. So 2 times to 3 times you can enter any value. So I am entering first 5. So minimum thickness it will keep it as 5 and click on update. So my design variable is updated. So then I will run this model. I will save this model as minimum dimension and save it as C clip and solve this model again and see what difference it will give if you put the minimum size or without the minimum size. So we will compare all the results of optimization with minimum member size or without minimum member size. Take some time to solve. So now you can see my analysis, or sorry, my optimization has converged and feasible design has been achieved. So I will click on results to view the result. I will go to XY plot, ISO, element density, say apply for the last iteration and decrease the value, say 0.3. So you can see the pattern is much more better as compared to the first pattern. So I will split the window into 2 to show you both the patterns. XY plot, element density, simple apply, ISO apply for the value of 0.3. So you can see with minimum member size control and without minimum member size control, the pattern which we get are 2 different patterns which we get. So if you change some of the parameters in topology optimization, you will get the output somewhat different or more accurate or more easy to manufacture that particular component. So in this way, we have ended with the tutorial of design concept for structural C-clip with minimum member size. So now We will move to the next tutorial. So we'll move towards the next tutorial, that is design concept for an automotive control arm. So this tutorial uses the OptiStruct topology optimization functionality to create a design concept for an automotive control arm required to meet the performance specifications. The finite element mesh containing designable blue and non-designable region yellow, as I will show you on the HyperMesh window. Part specification constrains the resultant displacement of point where the loading is applied for 3 load cases of 0.05 mm, 0.02 mm, 0.04 mm respectively. The optimal design would use a little material as possible. A finite element model representing the designable and non-designable material is imported in HyperMesh. Appropriate properties, boundary conditions, loads and optimization parameters are defined, and OptiStruct software is used to determine the optimal material distribution. The results, the material layout, are viewed as a counter of normalized density value ranging from 0 to 1 in the design space. Isosurface are also used to view the density result. Areas that need reinforcement will tend towards the density 1. The optimization problem for this tutorial is stated as: my objective is to minimize the volume. My constraints are: for the subcase 1, the minimum resultant displacement should be less than 0.05. For the case 2, it should be less than 0.02. For case 3, it should be less than 0.04. My design variable is the elemental density. In this exercise, we will see setting up the FE model in HyperMesh, set up the optimization in HyperMesh, and post-process the results in HyperView. So we'll open the HyperMesh window. I will close this. Click New and import the model in HyperMesh. So we will click on the open folder. And this is my model file with 3 components: non-design, design, and rigid elements. So this is my design, this is my model with the meshing and everything. So this is the hexa mesh 3D mesh model. Earlier we have seen the 2D mesh model. This is the 3D mesh model with the hexa elements. Now we will create the material and properties and assign them to the components. So we will start with creating the material in the same way. Now I will go a little quick on this part. So as we have already discussed many times related to the property and material, so I will go a little fast on this. So I will click on material, enter the material name, we'll say steel, define a color, select the type as isotropic, card image as matte 1, click on create edit, enter the values of E, nu and rho, click return, again click return to exit the material collector. So my material is defined. Now the next step is to define the property. So I will click on property collector, enter the property name as say property design, select a color, type as 3D because they are 3D elements, card image as P solid and material as steel, click on create, and another property for non-design, define a different color, type as 3D, card image as P solid, material will be the same, and create. So I have defined two properties, one is design, one is non-design, and assign it to the components. So I will click return to exit the property collector. Click on component collector icon, update the non-design one with the non-design property, update, and the design one with the design property, and say update. So I have created or assigned the properties and material to the element. So we'll cross check it with by material. So I will get the material color, and by properties I will get the property colors on the element. Now we will apply the loads and constraints on the model. So I will go to load collector, create the first load collector as SPC and click on create. So my SPC is created. Click return to exit the load collector panel. Now we will apply the constraint and create some more load collectors here, like brake, defining a color, corner, defining a different color, and pothole, another color. So I have created a 4 load collectors, SPC, brake, corner, and pothole. I will make the SPC as the current one and apply the constraints. So I will apply the constraint on this for the degree of freedom 2 and 3. For this, I will apply the constraint for the degree of freedom 1, 2, 3. And at the center of this model, I will apply the constraint here if I off this. So on this node, I will apply the constraint for the degree of freedom 3. So I have created 3 constraints. One is here. I will also increase the size so you can see. So one constraint is here, one here, and one here. Now we will apply the forces. So I will make the brake one as the current. Go to analysis, forces, go to create, select the node, enter the value as 1000. In x-axis we will apply the brake load and say create. Then we will make the corner one as the current. Corner force we will apply in y-axis of the same magnitude on the same node. And pothole also, we will use the same magnitude, but the direction will be Z on the same node. If I increase the size, say by 50, so you can see I have applied 3 loads on this point, that is X, Y, and Z, with a magnitude of 1000 each, 1000 Newton each. Then we create 3 sub cases for 3 different loads. So analysis, load step, brake, SPC as SPC, load will be brake and say create. Corner, SPC will be SPC, load will be corner, say create. And pothole, SPC will be SPC, load will be pothole, say create. So I have created 3 load cases also. So this is the basic static case which we have created right now, like MPCLL. So we create material property, assign it to the components. Then we create the load collectors, apply the loading conditions. So everything we have defined. Now Without running, I will directly move this model to optimization setup. So to define the optimization process, I will first click on return, go to analysis optimization and follow the same process as DRDO. First we will create and define the topology design variable. So I will go to topology, select the radio button as create, enter the value as design property, select the type as P solid, select the property as design, click on create. So on the model browser you can see my design variable is defined here. So all the elements organized in the design property collector are now included in the design space. Now we will define the volume and displacement response. So I will click return to exit the topology panel and go to response panel to define the responses. That is the next step in DRDO. Enter the response name as volume. Select the type as volume. Keep all the other parameters as it is and click on create. So my optimization response as volume has been created. Now I will create the displacement as the another constraint or response, sorry. Enter the response type as static displacement. Select the node on which the maximum displacement may occur. Select the total force, sorry, all the three displacement, that is total displacement. And click on create. So my second response has been created. Now I will click on return to exit the response panel and move to the next objective, next panel as to define the objective of my analysis. I will define the objective. My objective of this optimization process is to minimize the volume. Now I will define the constraints on the different displacements. So I will go to D constraint, enter the constraint name as say constraint 1. Check the box in front of upper bound and enter the value as 0.05. So my constraint is it should not go beyond 0.05. Response as displacement, load step as brake. For the brake it should not go 0.05. Similarly I will rename it to constraint 2. Upper bound to 0.02. Response will be displacement, load step will be corner, and say create. So my constraint 1 is not created. As you can see, you always have to check on the model browser whether it is created or not. So displacement, brake, create. And similarly the third one, it should not go beyond 0.04. Response will be displacement, load step will be pothole, and say create. So I have defined 3 constraints. So I have defined material properties, component, load collector, load step, as well as design variable, responses, D constraint, and objective. So my model is ready to perform the optimization. So I will go to File, Save as Model. Save this model as, create a new folder as Optimization. Go to Analysis, OptiStruct, keep the export option to all, run option to Optimization. memory option to default and click on optimization of the struct to start the solver window. So it is showing the error as topology optimization without minimum member size control. So I haven't given the minimum member size control which I have given in the earlier one. It's not an error. It is just giving a warning. So as you can see, my analysis has been converged and feasible design has been achieved. So I will go to view the results. I'll close this. So I will select the last iteration. Go to contour, element densities, everything method as simple. In ISO, say apply, and this is what my expected result should look like. If I on the features and transparency, so this much amount of material it has removed, and you can see it has come up with this design. Like for this constraint, my model should have this much amount of material. So you can move this and you can see how much material you want, or as per the manufacturability also you can check. So how much, how the design is easily manufacturable for you. So if this design is manufacturable, you can process with this design. So you can smooth it down. So this is the area of the material removal. So from here you can remove the material. If I split the window into two, S1 apply, I will split this window into 4, S2 apply, S3 apply. So I will see the displacement values for different load cases. So it has to be somewhere near my constraints values. So this is the brake load, it should not go beyond 0.05, it is satisfying. This is the corner load, it should not go beyond 0.02, it is still satisfying, it's very near to that. And the pothole one, it's also very near to that. So in this way, you can see the results. So OptiStruct not only give you the design area from where you can scoop out the material, but it also helps you to see after removing the material what will be the stress values, or what will be the what I can say, what will be the displacement values. So you can see the stress values also. So the maximum stress on this model is this much. So this is my topology optimization of automotive controller. So in this way I have ended with this tutorial. Now we will move to the next tutorial, that is increasing the natural frequency of automotive splash shield with ribs. So, a preliminary design of stiffeners in the form of ribs for an automotive splash shield will be generated in this tutorial. The objective is to increase the natural frequency of first normal mode using topology to identify the location of ribs in the designable region. So the optimization problem for this tutorial is stated as the maximum objective is to maximize the frequency of mode 1. My constraint is upper bound constraint of 30% for the designable volume, and my design variables is density of each element in the design space. In this exercise, we set up the normal model analysis in HyperMesh, post-process the initial results in HyperView, set up the optimization in HyperMesh, post-process the optimization results in HyperView, set up the final normal mode analysis in HyperMesh and post-process the results in HyperView, compare the final results with the initial results. So we'll see how to perform these. So we'll import the model of the splash shield, you can see, with component material property predefined. So my property is defined, my material is also defined. If I change the color will automatically get changed on the model also. So you can see it is changing the color. So I'll again go to components. Now we'll start with the setting up the normal model analysis in HyperMesh. We'll follow the same process. That first create the EIGRL load. So I'll first create the EIGRL card. Enter the card image as EIGRL and click on create edit to specify the values of V1, V2 and ND, that is number of modes. So we'll enter the value of V1 as 1, V2 as 3000 and number of modes will be 2. So we just created a load collector which defines data needed to perform real eigenvalue analysis, that is vibration buckling, and specified the solver to calculate the first two modes between the frequency range of 1 to 3000 Hertz. So we have just defined that. Then we'll click on return. Again we'll click on return and then we will create load constraints at the bold location. So these are the bold location, two bold location. We will create the constraint on these two bold locations. So first we will create a load collector as SPC with no card image because it will apply the constraint there. Click on create. Go to analysis, constraint, select these two nodes and constraint all the degrees of freedom. So I have constrained all the degrees of freedom on these two nodes. Now we'll perform a normal model analysis. For that we'll define the load step, also referred as subcase. Enter the name as frequencies. Select the type as normal modes. Check the box in front of SPC and select SPC. Check the box in front of method structure and select EIGRL and click on create. So in this way I have created the constraint. So I have created a load step as frequencies. I will click return. Save this file and run the model to see the frequency values. First analysis. Splash shield. Go to analysis, OptiStruct, run option as analysis, click on optimization, OptiStruct to perform the basic analysis. So my analysis is completed, so I will click results to see the results. Go to deformed and enter the deformed value as 0.1. So I have two modes, one is at 43 and second is 68 Hertz, and the eigenvalue is, if I say the maximum mean, so my eigenvalue is 300 for first, and for second it's also near the 300 value for the first subcase. So these are the values which I get from the basic model analysis. Now we go for the optimization process and see if we can increase, how we can increase the first mode of the splash shield. So I will click return to exit the OptiStruct panel and go to analysis optimization. We will follow the same process to set up the optimization in HyperMesh. That is, first we will create the topology optimization design variable. Go to create radio button, enter the design variable name as shield. Select the property as design, element type as shell. Will enter the base thickness as 0.3 because as per my problem definition, the upper bound constraint for designable volume is 30%. So I will give it the base as 3 because initially my base is 1. If I go to show you that, you can see also. So I will give the initial as 0.3, the same as the regular one. So a topology design space defined shield has been created. All elements referring to the design property collector are now included in the topology design space. The thickness of these shells can vary between 0.3 base thickness defined above and maximum thickness defined by the T field in P shell card. The objective of this exercise is to determine whether to locate ribs in the designable region. Therefore, a non-zero base thickness is defined, which is the original thickness of shell. The maximum thickness, which is defined by T field on the P shell card, should be allowable depth of the ribs. Currently, as you can see, the T field P shell is set to 0.3. We will change it to 1 so that the ribs of the maximum height of 0.7 units can be obtained by the topology optimization. So we will see where we have to exactly create the ribs to achieve that. So I will change the thickness value from the base thickness to 1. So it can create a ribs up to 0.7 mm. So I have changed the property or the thickness of the component. Now the next step is to define the responses. I will go to create the response. First response is frequency 1. Select the type as frequency. For the mode 1, click create. So my frequency as the response is created. Now the second is volume fraction. Select the type as volume fraction. Keep all the other parameters as it is and click on create. Click return to exit the response panel. Then we will define the objective. So my objective is to maximize the first frequency mode. From the load step, we will see the first frequency value it will take. So my objective is to maximize the first mode of the frequency. Then I will define the constraint. A response defined as the objective cannot be defined as constraint. In this case, you cannot constrain the response frequency 1. So an upper bound constraint is to be defined for the response volume fraction. So we will define the constraint for volume fraction. So I will enter the constraint name as volume constraint. Enter the upper bound value as 0.4, that is 40%. It should not go beyond that. And select the volume fraction as the response and click on create. A constraint is defined on the response volume fraction. The constraint is an upper bound with a value of 0.4. The constraint applies to all sub cases as the volume fraction response is a global response. In this exercise, we are allowing the topology optimization to use additional volume with which it can come with ribs constraint. So I will click return. Again I will click return to exit this panel and save the file. Second analysis, that is the optimization. Go to analysis, run option as optimization and click on OptiStrat. So click on results. So with this results, we can see exactly where we need to put the ribs to achieve that particular design. So the last iteration we will select element densities, simple, and apply. So these are the regions, like here we have to put one rib on this side. So we have to put a rib from this end to this end. Similarly from this end to this and this end to this. So it is showing the area where we have to put the ribs. With this, whether my model is giving the appropriate results or not, let's see that. So we'll go to open model, second analysis, H3D S1 and say apply. So for the iteration, last iteration, my eigenvalue mode should be greater than the 300 value. So you can see. So my first mode for the same frequency range is coming as same. You can see that. So with this, if you put ribs here or change the thickness, the frequency value changes. We'll again see after putting the ribs what will be the results. So I will close this. I will close this also. Click here new and bring down that model. Which is having that files. So I will go to import. I will import that model with the rib pattern which my solver is showing. Say import. So here you can see I have put the ribs as suggested by my software. You can see. So these are the areas where my software suggested me the ribs, like this area, this area, this area, this side, and in between here also he have suggested. So I have put some ribs here. We will save this file. Go to analysis, OptiStruct, and say OptiStruct, and view the results. So if I change the mode shape and see the results, so you can see after putting the ribs, my first mode is coming larger than the previous one where I haven't put the ribs. For the same frequency range, I can show you that also. So we can check whether the frequency range is same or not. So you can see the frequency range is exactly same. So there is no change in the frequency range. First, just by putting some ribs, my first mode is increasing. That's what my objective is. So in this way, my software helps to improve the design as per my requirement. So in this way, we have ended with this tutorial. Now we will move to the next tutorial, that is, I will close this. Close this too, click new. Then we'll move to the next tutorial as control arm topology optimization with draw direction constraint. So we will see how to perform that. So in this exercise, we'll perform topology optimization using draw direction constraint on the control arm. The finite element mesh containing designable and non-designable region is available in the model. I'll show you that. The following exercise includes setting up topology design variable and draw direction constraint in HyperMesh, setting up the topology optimization in HyperMesh and post-process the results in HyperView. So we'll move to the HyperMesh. So I'll open the HyperMesh, go to open. So this is my model with components, load collectors, load step, material, property, everything is defined. This is my control arm, where I have already predefined everything. I will directly go to the optimization process and see how to apply the draw direction constraint. So if I am applying a draw direction, how we can apply that. So the draw direction constraint allows the casting feasibility of the design so that topology determine will allow the die to slide in a given direction. This constraint are defined using DTPL card. Two draw options are available. The option single assumes that a single die will be used, and the option split assumes that two dies splitting apart in given draw direction will be used to cast the part. So we go to analysis, optimization, we will directly move to the optimization processing. So click on topology. We'll first define the design variable as dv1. Click on the property and select design. Select the type as p solid. Click on create. So my design variable is defined. Then select the radio button as draw. Here you can see single or split. Single stands for one die, split stands for two dies. We'll select the option single. The option single assumes that a single die will be used and it slides in a given draw direction. The anchor node and the first node defines the draw direction. So we'll click on anchor node and enter the node ID as 3092. Then the first node as 4716. So this will be my draw direction. In this way my draw will enter. Under the obstacles, click on property and select non-design. So it should not take the non-design part also. So that's why this select the non-designable part as obstacle for the casting process on the same DTPL card. This preserves the casting feasibility of the final structure, and click on update. So in this way I have defined the draw direction. Now we will define rest of the things like create the responses. So we will create the response as volume fraction. Select the type of the volume fraction as response type as volume fraction. Click on create. Enter COMPL compliances. Select the response type as weighted compliances. Click on the load step. Check the box in front of both the load cases and click return. So I have put the basic load cases, so it will take both. And click on create. So if you want to review, you can review that also. So compliances, load cases are defined. Now the next step is to apply design constraints on the volume fraction response. So we'll go to deconstraint panel. Enter the deconstraint name as constraint. Check the box in front of upper bound and enter the value as 0.3. Response type as volume fraction and click on create. So my D constraint has been defined, and my objective is to minimize the compliances. So I'll go to objective, select minimize, response type as compliances, and say create. So my objective is also defined here. So I will save this file and run for the analysis. So go to analysis, OptiStruct. So here you can see weighted compliances it is and volume fraction it is creating the different iterations. The final iteration will be the best possible result for as per our constraint and objective. So it will keep on solving it by creating different iterations. If you maximize this, you can see the values of iterations and everything. So you can see it's on 13th iteration, then on 14th, 15th iteration. So it's trying to violate the result as per our required constraints and objective. So now as you can see, my analysis has been completed. So I will click on results to view the results of the draw direction constraints. So select the last iteration, contour, elemental density, say simple, go to ISO, apply, save for 0.25. If I on the features and transparency, you can see the draw direction constraint. With the draw direction constraint, it comes out with this result. If I enter the value as 0.5 or 0.3, it will also come up with this. So these are the areas from where we can scoop out the material. With the required design what we want. So in this way we have ended with this tutorial. So now let's move to the next tutorial, that is spot weld reduction using C-weld and 1D topology optimization. So in this tutorial demonstrate how to perform 1D topology optimization. The model is a simple welded hat section. The welding is modeled using C-weld element. The hut.hm file can be found in the installation directory as it's given the path. The objective is to minimize the weighted compliances through all three load cases. The volume fraction of the weld component is limited to 0.3. The design space is the spot weld component. The following exercises are included in this tutorial. Define the design space, setting up the optimization problem, and post-process the result. So we will move to the HyperMesh window to open the model. So this is my model. Here we will see the C weld elements, you can see. So we will check the optimization of C weld elements. So we'll start with the defining directly, because my material property, load collector, load step, everything is defined here. So we will directly move towards defining the load collectors. Defining the design space. So go to analysis, optimization, topology, enter the design variable name as topology, select the type as C weld or P weld, click on properties and select P weld 500, select, click create, then click on return. So my design variable is defined. Now we will define the responses. So I will click on responses, enter the response name as volume fraction, type as volume fraction, click create. So my volume fraction as the response is defined. Or in this we will select property as P weld. Only for that we will create a response, and we will create a volume fraction as weighted compliances, the other one, and select the weighted compliances, click on the load step and tick all the 3 load steps. Change the weighting factor of subcase 2 and 3 to 100. So they will have the majority of weightage for the optimization process. During the optimization process they have the majority of the weightage. So this increases the influence of 2 bending load case versus the torsional load case subcase 1, which is kept at 1. So the influence is higher. If you want to put it like that, you can also do like that. Now we will define the constraint. My constraint is volume fraction. Check the upper bound as 0.3. Constraint value as volume fraction. Click create. Click return and define the objective as to minimize the, I haven't created the weighted compliances. So objective as weighted compliances, create. So my objective and constraint has been defined. Click return. Click on Opti Control and select the discrete ID and enter the value as 20 and objective tolerance. So this increases the penalty factor in the density method only for 1D element to achieve a discrete result. So discrete ID will help us to do that. And penalty factory of an objective tolerance, check the box and enter the value of 1.0 e to the power minus 5. So this reduces the objective tolerance that is checked for convergence. So click return, again click return We will save the model. Analysis, OptiStruct, and run the solver. So my analysis has been converged. So I will view the results. For the last iterations, we will see the elemental densities. So these are the values. If I go to ISO, exactly where we don't require the welds, you can see that from here. The red ones are the mandatory, the blue ones which we don't want these weldings. So in this way, you can also figure it out where exactly you want the welding or you don't want the welding. That is also possible with the optimization process. So we'll move to the last tutorial of this training session. I will close this one. Click new. So the last tutorial is pattern repetition using topology optimization. This tutorial demonstrates how to perform topology optimization using pattern repetition. The model is a rectangular plate with a concentrated force on one edge and two constraints on the opposite edge. Two other rectangular plates with a scaled size of 0.6 and 0.3 from the original plate, with force and boundary conditions applied in different directions, are also modeled to highlight the difference between the topology results with and without the pattern repetition. The objective is to minimize the compliances of a single subcase. The volume fraction of the design space is limited to 0.3. The design space are the three plates. In this following process, we cover retrieving the OptiStruct input file, setting up the optimization problem without pattern repetition, post-process the results without pattern repetition, adding the pattern repetition card, and post-process the new results with the pattern repetition. So I will see this is mainly used in the airplane wing ribs, and if a model is of the same shape or structure but with scale model, you can do an optimization for one plate or one of the component and do the same, get the same pattern on rest of the model. So I will show you how to perform that. So I will import the model. So this is my model file with different constraint locations. I will go to constraint on the label. So these are the constraints. Different constraint location, different direction forces. I will apply the optimization process on one of the plate and see the results for the rest. So we will start with setting up the optimization problem without pattern repetition. So we'll first create the topology design variable. So I'll go to analysis, optimization, topology. Enter the design variable name, say dv1. Select the type as P shell, property, select the first. Click on create. Check on the parameters and enter the minimum dimension to 2. Click on update. Similarly, I will create 2 more design variables for second. Create parameters, update, and the third one, third, create parameters, update. Then we create the responses for volume fraction and compliances. So I will go to response, enter volume fraction. Select the type as volume fraction. Select total and click on create. And the other one is compliances. Select the type as compliances and click on create. We'll define the constraint for this model. So we'll go to constraint, volume fraction. Check the box in front of upper bound and enter the value as 0.3. The response as volume fraction and create. Then we'll define the objective as to minimize the compliances for the load case sub and create. So in this way, I have defined the optimization process without pattern repetition. So we will see the results without pattern repetition. What will be the post-process results of the optimization process? First, optimization. So analysis, OptiStruct, keeping all the parameters as it is, I will click on OptiStruct to solve this model. So go to analysis, results, click on results to view the results of the analysis done. We'll see what pattern we have achieved with this optimization. So iteration last, element density simple apply, in ISO scoop out the material. Beyond the features, so this is the pattern which we have achieved, but it is not same. You can see the direction is changing. It's changing as per the force application. So if you want to manufacture this, we are going to manufacture the different designs, and entirely is a different thing. So if it's easily manufacturable for you guys, you can do that. But for some certain process that they want the same pattern to be manufactured. So if someone wants same, then we will see now how we can do that. So in the same model, we will see how we can do the pattern repetition. So I will go to tools, numbers, and of the load collectors. So I can put the numbers on. Select the nodes to define a particular plane. So nodes by ID 1329, 66, 6, 46. So these are defined in the tutorial. You can get it from there. So we are just defining the plane. Once I will add, you will see what are these nodes for. they are basically to add the nodes. So I will say on. So you can see the number. So to define the pattern repetition, we need a number to be specific or a same plane. So I'll go to analysis, optimization, topology, select the last column as pattern repetition. Click on design variable and select design variable 1. Make sure the switch is pointing towards the master. Toggle the systems to coordinate. Click the first button and choose 6. Then 46 and so the 132 is this one, design variable 1, and 132 is the third, and 66 is the anchor node. Click on update. So this will get updated. Then select the second design variable, make it as a slave. And master is pointing to DB1. SX, the scale factor value, enter as 0.6, and Z will be 1. Then first will be this, second will be this, third will be this, and the fourth one, anchor node, is this one. Click on update. Similarly, design variable 3, slave, design variable 1, SX.3, SXY.3, SZ to 1, first, second, third, this, and update. So the above modification identifies that the first DTPL card with ID 1 on the first component as the master, the DTPLs of the ID 2 and ID 3 are slaves on and the dependent on DTPL of ID 1. The second component is the scale 0.6 in both X and Y axis. If I put in XY, you can see. While the third is the scale of 0.3 in both X and Y axis with respect to the first component. So in this way, we have defined the pattern repetition. Now we will save this model. Save it, go to analysis, OptiStruct, and solve this model. So it will start the solver window. I will again quickly show you how we have created. Go to analysis, optimization, topology, pattern repetition. First create the design variable 1 as the master, selecting 3 nodes, 1, 2, 3 for the plane. Third as the anchor. Then the second one as the slave of first master 1. With the scale factor of XY, the scale factor is put here, and the same anchor node as the first. Then the third one will be the scale factor of the earlier one, the master one, how much is the scale factor of it, and the 3 coordinate values. So my analysis has been converged, so we'll view the results. That's the only thing we have to do to get the pattern repetition. So now we will see the results from the last iteration. If I go to ISO, apply, let's say 0.15. If I off the features, you can see they all have the same pattern with the scaled magnitude. So in this way, we have ended with this tutorial. So if you have any questions or any suggestions related to this, feel free to ask, or you can contact me via edu-support@india.altair.com. If you have any comments or any suggestions to improve these online training sessions, feel free to do that too. So in this way, we have ended with the online training session, day 6, that is optimization, part 1. Sooner we will go for the next part of the optimization process. Thank you very much for attending this session.